Good morning, everyone. Welcome to DCT 302 class number 6. So we've all had a break, and I hope you enjoyed the week off, and now we're back at it once a week for 5 weeks. So let me just say halfway through the class that I've really been enjoying doing this, and I'm especially enjoying the feedback. I've been out there in the forums, and there's been 5 or 6 forum threads that are good. I would like to pick up on a couple of forum threads or questions that people had, and I'd like to do that, try to do that online. So I think, let me scroll back. I think, Ali, you're asking if we could talk about QuickTime Gamma. And maybe we'll do that this class, maybe we'll do it next class. In fact, I think we'll do that next class. So let's push the gamma discussion, the gamma shift, the gamma mismatch issues on to the next class. So Ellie, I hope you can hold out for that. There were a couple of other questions in the forums, which are kind of open questions. So let me see if I can pull that up. Right, that's Peter Rixner's question about P3 gamut and projectors. So I'll deal with that one right now. And also, as always, I'm open to questions and interruptions during. And then concerning questions and feedback and interruptions and stuff, I'm delighted that so many of you took the time to do the SurveyMonkey review of the first 5 classes. I've certainly scanned those comments, as has John. And you've made some really good comments, and I really appreciate your taking the time to do that. And I will address a few of those things. Now, there were a few of you who were not really happy about material duplicated from 301. And I must say that that's a little bit of a challenge for me as a presenter, because I can't be guaranteed that all of you were have experienced 301. So, you know, I'll try to keep the technical level a little higher than 301. The rest of the remaining classes, but a little bit of duplication. Some of the material is really hard anyway, and so I'm thinking that on some of it, it's not so bad to cover it again. But as I say, I really, really, really appreciate the comments on the survey of the course. So thanks for that. So what I'd like to do today is talk in some detail about 3x3 matrices. So you'll remember from class 1 that an IDT in the ACES workflow really does 2 things. One is that it inverts the electro-optical characteristic of the camera, or you could call that the hardware curve that's applied at the camera, or I should say typically applied at the camera. So this would be one of the various log curves for the cine mode log cameras, or even potentially a power function curve or gamma correction curve if it's more of an HD shoot. So the camera imposes those curves in hardware simply in order to squeeze the 12 or 14 bits from the camera analog to digital converter into the 10-ish bits that are typically used for recording. Now, of course, we know that for really high-end cameras, and the F65 would be one example, there is a capability to record the camera sensor signals directly on the media, although with a little bit more data rate and data capacity required. So in that case, the IDT does not have to invert the curve. The second part of the IDT is a 3x3 linear matrix that basically converts from camera let's call it native camera um, device space, and you could loosely call that camera RGB space, into ACES RGB, which is defined in a very specific way that we've talked about in previous classes. And today I'd like to talk about how you compute those 3x3s. And I did give this story in DCT 301, but I'll give this story again pretty fast, pretty highly technical, and specifically directed to ACES. So that's the plan for today, is to talk about that. And depending if there's some time left over, we might talk about some grading issues, lift, gamma, gain, and shadows, midtones, highlights. So if you've got interest in those grading things, then maybe you can indicate in a chat message that you'd like to talk about those. And we could talk about those today. We could talk about them later. Okay, so let's first, though, address a question in the forums. So it was a question from a couple of you, D. Boyce, I'm not sure of your first name, but also Peter Rixner. So Peter is commenting in the forums that he supposes that today's cinema projectors are displaying DCI P3, and that is absolutely the case. But Peter wonders, how could we see a bigger gamut while working in the ACES world? And the answer briefly is all of the deployed cinema projectors today, that's up at the professional level, D Cinema, mastering and exhibition, they are all P3 plus or minus 0. So that's a gamut wider than 709, but not as wide as ACES. Well, nothing can be as wide as ACES because ACES has got primaries that lie outside the horseshoe. So you cannot even make those ACES primaries physically. They are non-realizable or non-physical. You could use either of those terms. So when you're working in ACES space, you're working in a kind of theoretical, abstract gamut. And for any sort of display of that, you need some gamut mapping and some color transform machinery. And that's one of the purposes of the ODT. So then Peter is asking further, did I really say that all projectors are at wider gamut, or do I mean professional projectors? So I mean professional projectors. So Peter's asking, how could I get to display wider gamut? My projector is always fed DVD or Blu-ray. Well, there are pieces of consumer electronics that do wider gamut than 709, but they almost all do so by warping colors that were mastered at 709 into more colorful colors for display because they think that consumers like more colorful colors. And you've really got two choices there. I mean, one choice is you can decide to be conformant to the standards and get a calibrator in to calibrate your projector to haul it back into 709. But the other thing you can do, you can potentially get the assistance of a calibrator to set up your lower cost non-D Cinema qualified projector to be wider gamut than 709, and you know what the gamut is and you know what the primaries are. And you would do that by calibrating the projector to a color space wider than 709. But with a commodity projector that you might use in a VFX facility, like a sub $20,000 projector, it probably will not go out to DCI P3, but it still might be useful for working space if you're working on VFX for a movie. So At the home cinema level, you're not likely to be able to do DCI-P3, but you might get reasonably close. So then I hope that addresses that question. And if not, just go, make some comments on that thread in the forums, and I'd be happy to talk about it some more. Okay, so with that, I'm going to very, very quickly go through a set of color sensing and display slides. And I don't think I've ever used these in public. Well, this isn't really public here, but I've never really used these for an official presentation before. But I would like to just very quickly go through these and just to lay the background for how we build the 3x3s. And the 3x3 linear matrices, they're used not only at the front end, like a big part of the IDT and the ACES workflow, but also at the back end for calibration. So let's run through that material, and then we'll get to the math. So, as I say, these are not slides for public consumption, but I think you guys will enjoy them and not give me a bad rep for using them. So in terms of display technologies, we've got direct view and projector technologies. CRT is now gone in both places. For direct view, plasma and AMLCD are in the mainstream. OLED is very interesting. For projection, there was a technology called grating light valve, originally developed and commercialized by Silicon Light Machines. Well, I shouldn't really say commercialized, because before commercialization, the technology was sold to Sony. And it's apparently parked, not in use. It's a micro electronic mechanical machine. It's a MEMS technology like DLP, but not commercially available. DLP is the big deal in projection, of course, but active matrix LCD is used in both. So your projector might have an LCD panel, it might have DLP. LCOS, as in Sony SXRD and JVC ILA, it is also an LCD technology, but instead of liquid crystal on glass with a very low tech transistor technology on the glass, the LCOS is built on silicon backplane, but you have to reflect light from the silicon chip, because silicon is opaque to light. The most of the lower cost projectors have an LCD panel where the light is just traveling through the LCD. It's just sort of a small version of a direct view panel. So those are the display technologies available. And now, one way to get color is the old-fashioned sequential color way that allows you to use one panel instead of three. So one DLP chip, and the technique is not useful for LCDs, basically. And I'm showing this as if there's a spinning filter wheel. There is actually a spinning filter wheel on many of these devices, but there's now the capability with LED illumination in projectors to flash the LEDs red, green, blue. And that's an up-and-coming way to do a one-chip field sequential projector. But with fast motion, you leave color fringes. So generally not a good idea for fast moving material. Although for 24 frames, it generally works just fine. But we at the professional end would prefer a 3-chip, either 3 LCD or a 3-chip DLP projector. Obviously, color involves absorbing certain wavelengths. So basically, as we talked about in an earlier class, class 4, I think, you can consider the wavelength band from 400 to 700. You can absorb short waves to make something look yellow. You can absorb medium waves, so various amounts of absorption. And you can absorb long waves, and you can absorb, obviously, combinations. So I like to think of this as in an additive display producing red, green, or blue, or absorbing cyan, magenta, or yellow. And those are the complementary colors. But instead of absorbing, there's another scheme where you can have a filter that uses interference phenomenon. So basically, this is a filter where the layers are put on the filter approximately, well, a quarter or a half of a wavelength of light. So really, really, really thin filters of special material, some sort of magnesium oxide or magnesium fluoride usually. And this produces a piece of, well, it's coated on a piece of glass, because obviously if it's only a few wavelengths thick, you can't have any physical strength. So coated onto a piece of glass. And this produces a filter which takes the wavelength band and reflects some of that energy and transmits the rest. It absorbs nothing. This is called a dichroic filter, and this is used both in cameras and projectors. And one way to use dichroic filters in an RGB system is just have two of them. So take light potentially of all wavelengths, separate out the short waves, call it blue, then separate out the long waves, call it red, whatever's left over is green. And this is the basis for 3 CCD cameras, the typical video camera even today. You don't need a mosaic pattern. And the reflection characteristics look something like this. So separate the blue, separate the red, what's left over is green. And you can also use the technique for projectors. And here I've sketched an old CRT projector, but obviously this can be DLP or LCD as well. Now, the classic way this is used in a video camera is with the Philips prism. So those dichroic, the prism does not separate like Isaac Newton would have recognized. It isn't the prism itself that's splitting the different wavelengths into different directions like Isaac Newton. Instead, prism is just a word that's used by optics engineers to refer to a chunk of glass. So the prism in an HD camera is a chunk of glass onto which these dichroic filters have been coated onto certain surfaces of the chunk of glass. So the optical separation happens with the dichroic filters. The prism is just a convenient mount for the filters. And also the prism is used to reflect light into the different sensors. I've shown them as if they're tubes here, which they obviously were in the old days, but today they would be CCD chips actually cemented right onto the surface of that glass prism. And it's a tricky alignment thing because you've got to have those CCD chips or CMOS chips cemented really accurately in register with each other. So that's a way a 3-chip camera is used today. And obviously the advantage of a 3-chip camera is you get all 3 signals coming out of the sensors. Well, let's nix the tubes here and just have CCDs. So you've got these 3 signals coming out and they're perfectly in register. And they're basically optically superimposed. So there's no need for any kind of demosaic bearing, any of that. So that's the use of dichroic filters at capture time, and you can also use dichroic filters to display, and that's what a DLP cinema class projector does. So here's a slightly more accurate diagram of what's going on in the prism, and I show you this diagram to show you that here's the prism that separates out the blue. And so we're going to cement the blue CCD to this surface of the prism. So the filter separates blue here, but we use the prism to do total internal reflection. We don't need a mirror. And this is because you can arrange that the prism reflects, and it depends upon the index of refraction of the glass and the angles and so on. So there's very tricky optics that takes place. Here there happens to be an air gap, and that's a very precise gap. The filter that separates red is here, so there's a dichroic coated on this side of this prism. Total internal reflection is used here, and the red sensor is cemented to this part. The green sensor is cemented way back here. Why is it so far back? Well, because the optical path length to get to each of the three sensors has got to be identical. And the path length to get to blue has got to have all of that distance inside that prism. And the path length to get to red has got to include this traverse through the blue prism, this and this and this traverse through the red prism. This has got to add up to the same amount. Now, what that means in terms of optical design is the closest you can get the flange for the lens is about here. So this is basically your camera mounting. So if you pull the lens off an HD or 3CCD camera, what you see is the front surface of the prism. But the sensor is way, 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 way back here. And so you build the lens with several elements and a complicated piece of lens business here. But from the back of the lens, from the flange to the sensor, so this distance, which is called the flange focal distance, and this is all about the back focus of a camera, it's incredibly long for a 3CCD camera. And the amount of light you can collect, it depends upon the diameter at the back of the lens. And that basically limits the F number of the lens. And you might be saying to yourself, wouldn't it be nice if we could have the sensor right up close to the lens so we can have a larger collection angle? Well, that's a mosaic sensor. It doesn't have as long a back focus, and it has as wider aperture possible. Okay, so so marching on from dichroic, the dichroic arrangement for a DLP is even more complicated because in the case of a DLP, you've got to ship in light, which illuminates the three DLP devices. And then you've got to arrange when that light is reflected that it doesn't get reflected back into the light source, but goes out to the projection lens. So there's a very, very complicated arrangement of optics in a DLP projector, but it's all very much stemming from that Philips prism idea invented about 40 years ago. Now, in terms of the color parameters at display time, you might think, well, the simple way to do this would be if you've got a light source that's relatively wideband, like you've got a xenon, as in a big projector, or a UHP lamp, which is in a sort of somewhat smaller projector, like a home theater class projector, or a projector that you would use in a small VFX room. They've got rather uniform distribution of energy all the way from 400 to 700. So you might think, well, the way we use that energy is separate it into shortwave, long wave, and medium wave, and use that. But the thing is, if you do separation like that, you get primaries which are not really very saturated. So it's basically perfectly good for 709 class projectors. But if you want to have really good D Cinema class color saturation, and the blue happens to end up at more or less the same place, then you need to move those points out closer to the spectrum locus. And one way to do that is to have light which is missing that power in the cyan and yellow regions. And so we talk about DLP cinema class projectors that have got a cyan notch or a yellow notch, which is removing energy from certain parts of the spectrum in order to get wider gamut. However, that means they're not using all of the light from the light source. And I hope you're now taking one look at this diagram and thinking, well, if we had LED light sources tuned to the appropriate 3 wavelengths, that would generate wide gamut and not throw away any light. And that's the hot tip. So LED light sources would be great, and laser sources for purposes of gamut would potentially be even better. But lasers, well, as we all know, IMAX is interested in lasers. Barco's interested in lasers. Well, even Christie has demonstrated a laser projector. So lasers are the hot tip, but they're going to be very, very, very high end. And then how we do this gamut mapping from P3 out to laser, well, that's an open question. So IMAX can pull that off in the short term because they're in a very closed business environment. But everybody else, it's basically emergent technology. Now, when you look at this diagram, I want you to start thinking about what if we had a camera spectral sensitivities that looked like that. And even though this sort of scheme works perfectly well on a display, this does not work for a camera because we cannot have a camera that's missing complete bands of the spectrum because we might have scene information like reflectances and objects in the scene where the color variations that you and I see come from variations in this particular region of the spectrum. So you have to go and look at what are the spectral sensitivities of the human vision system, and they're really dramatically overlapped through the whole spectrum. So for sensing, we've got to have spectra that's got overlap, very carefully constructed, even though on a display you can generate those colors with 3 lasers, and we're stimulating those 3 channels of vision. And so by just varying the amounts of power in those 3, we can stimulate a huge range of colors, not missing anything. So the key point to take away here is that the camera relative spectral response curves, which are a function of wavelength, are absolutely not the same thing as the spectral power distributions at the display. Nobody, you just can't use the same curves. This is a curve of sensitivities. This is a curve of spectral power. They're not the same thing. So even though we plot both of those on plots that look roughly similar, because they always run from 0 to 1 on the y-axis and 400 to 700 on the x-axis, they're not comparable. Now, one way in a display to achieve wide gamut is to have more than 3 primaries. And we can see where we're headed here in the long term. The laser primaries allows us a huge gamut, but you have to use these very special light sources that only produce energy in a very limited portion of the spectrum. If you've got a xenon or a UHP lamp that just has energy rather evenly distributed across the spectrum, one way to get wide gamut out of that is to have a whole bunch of primaries, like in this case, 5 of them. So this is called multi-primary, where multi just means more than 3. And the effect on the chromaticity diagram is basically produce primaries at various points, and then you stitch them together in some kind of polygon to get the gamut coverage. But as lasers become more economical, multi-primary becomes less interesting. And another example I can give you here is Sharp, which basically produced direct view LCD screens with 4 primaries. They call it Quadtron. And it's got a yellow primary. So the Sharp example is one idea of a multi-primary system with a 4th primary. Honestly, they picked the wrong primary, though, because it really doesn't improve the gamut compared to what you can get with classic RGB LCD. It does, however, lead to brighter pictures. There is an efficiency gain in taking the Sharp approach. So then coming back to the main point for today, and now we get into the math. The main point is these camera sensitivity curves are absolutely not the inverse of the display spectral curves. They're related, but they're not just an inverse. So now we have to talk about the math of how they're related and what that involves. I think that's all I have to tell you on that front. So let's get rid of that. And now we'll go to details of 3x3 space. This is basically color transform theory. You've heard about these standard primaries in previous classes. The wide gamut primaries that are interesting are Adobe RGB 1998, interesting because we can buy displays today that do this. They're basically RGB LED illuminated LCDs. And it's widely used in professional digital photography and graphic arts. But it's a pretty decent wide gamut scheme that you could absolutely use for VFX as well. Now, you'd like to get out to DCI P3 space, and you can buy displays from, well, you can buy it from HP, you can buy it from ASO, and, well, if you really want to, you can buy a Sony E250. All of those displays will do DCI P3 space. They're direct view LCD displays, but the E250 is, of course, expensive. And the other standard wide gamut primary is DCI XYZ. Well, that's just the whole triangle and then some. But it has colors that are non-physical. And also, we should mention ACES space, which is basically the same sort of space, but using a different blue primary way down here. And we'll talk about that as we go. So another set of standard primaries new to my chart is ACES. Whoops. So we characterize primaries by the little x, little y, little z coordinates of the 3 RGB. And we assume that it's additive mixture. So that we know that cyan is always green plus blue. It's just straight up additive. That's the math. Now, there have been some primaries, like the early DLP projectors, like even for the release of Star Wars Episode 2, used a scheme called P7V2. And this is, even though the number is bigger, this is really the predecessor to P3. P7V2 was not an additive space. So cyan was not equal to green plus blue. And this scheme was used because the grading in that color space kind of mimicked film grading, but that turned out not to be a good idea. We don't use it today. So there's still the DLP cinema projectors have got a setting for P7V2. You can dial it up, but don't do so. It's an obsolete space. Don't use it. Now we specify the additive spaces in terms of the XY coordinates of their red, green, and blue. We also need to specify white because different mixtures of red, green, blue create different white points. You need to standardize that. And for my example, I've chosen D65, although the P3 white point is much closer to D61. So you can choose different white points for different applications. Here I've shown the little Z coordinate, but don't worry too much about that because if you've got X and Y, you can always make little z. It's just 1 minus x minus y, which you can confirm by looking at the arithmetic. But for mathematical purposes, it's useful to have this 3 by 3 matrix. So you characterize the primaries with that scheme, and those are exactly the little x and little y coordinates on the horseshoe diagram. So if those coordinates lie within the horseshoe, you can make that primary physically. If they lie outside, you can't. It's a non-realizable color. Now, the place we want to get to in the next 15 minutes or so is how do you make these matrices which relate RGB of a particular flavor in linear light space. So there's no primes here that would indicate nonlinear space. These are linear light, not linear like a DIT would say, but linear light. How do we get to XYZ? Because this big X, big Y, big Z is the mathematical space that links all of the other spaces together. So the way to get from RGB to big X, big Y, big Z is through a matrix. And we're going to learn today how to make that matrix. And I'm sure you're all familiar with the dot product notation. Now, if you've got that matrix to go from RGB to XYZ, you can just take its inverse to get from XYZ to RGB. Now, this sort of transform using 3 by 3 matrices will give you a straight colorimetric transform guaranteed to produce exactly the same color. Nothing here does gamut mapping. And you can see from the existence of some negative numbers in these matrices that you can potentially come from a color specified in XYZ and generate negative numbers over here. And negative numbers in 709 space would lie somewhere outside the triangle. And normally you would just clip those numbers. So if you want to do something more sophisticated, you have to go and do gamut mapping. These transforms are straight colorimetric transforms. How do you make them? Well, it's math. And so I'm going to assume that most of you just want to know the flavor of this mathematics, and a few of you might actually take on the task of computing these matrices. But you would normally expect your grading system vendor or your color calibration system vendor to do this math for you. But I'm going to very quickly go through the math just to give you a notion of what sort of things you would do to make them. So you start with this chromaticity matrix C. It's just the little x, little y, little z coordinates of the red, the green, and the blue. And I always make these matrices so that the elements that lie together that are units are in the columns of the matrix. This is a classic linear algebra technique. The basis vectors are in the columns of the matrix, not in the rows. I mean, obviously, you could just go do a transform here if they were the wrong way around. But I just prefer to put the basis vectors in the rows. So the C matrix is the chromaticities. you go and do a little bit of linear algebra incorporating the white point. So we're incorporating little x, little y, little z of white. And we do a normalization to the big, I'm sorry, to the little y, and we dot product that with the inverse of the chromaticity matrix to get 3 normalization factors called J. Now, the luminance for that particular set of RGB is just the J vector element by element times the little y coordinates of the primaries. Now, the luminance coefficients are important. So we know that taking one step back to the 709 flavors, the luminance coefficients are the middle row of that matrix. And it's the luminance coefficients that are telling you that blue, when you form this dot product, only contributes about 7% to luminance. Green contributes 71%, red contributes 21%. Now that's all in the 709 flavor, and some of you may know these numbers: 0.299, 0.587, 0.114. Those are the luminance coefficients for the original NTSC SD system. But today we really want to use 709. Those are the luminance coefficients. That's simply the middle row of the RGB2 XYZ matrix. And you compute that using this math. You can then go and compute the rest of the matrix by doing this. So it's just a couple of dot products, and it's honestly pretty simple math. So what we do is we take the dot product of the chromaticity matrix with the diagonal matrix having those scaling factors. That forms a matrix T, which is then the matrix that transforms from a particular flavor of RGB to a particular flavor of XYZ. I'm sorry, there's only one flavor of XYZ. Take that back. So we can come into this sort of standard canonical form of XYZ. And now if we want to map into a different flavor of RGB, all we do is take the source RGB, map it to big XYZ, and then map that through the inverse of a second T matrix for the destination. That forms the destination RGB. Now, the example that I showed a few moments ago was the matrix. Oh, I'm sorry, I'm losing track. So one example is to go from 709 HD flavor, other way around, from SMPTE RP145, which is basically standardized SD space. So SMPTE RP145 describes SD today, the primaries, and 709 is, of course, HD primaries. So how do you get from one to the other? This is the matrix. Now, this, you can see, has got very small numbers off the diagonal. Well, as big as 5%. So if you're just to take 709 RGB you could say, well, that's pretty much similar to SD RGB. We can just take SD RGB values and we'll just call them HD, close enough. But you'll have an error of about 5%. To get rid of that error, you need to perform this transform. So whenever you want to ingest SD into 709, you really should do this transform. But this is an example where the numbers off the, the diagonal is pretty much 1. Well, 94%, 96%, 1. But there are some terms off the diagonal. If you don't do this matrix, you'll generate some errors. But you might ask, Okay, so that's to get from SD to 709. What about going from ACES to 709? Well, that also involves a 3 by 3 matrix, but now the numbers get different. And let me show you what those numbers are. Um, okay, here they are. So this is to go from ACES RGB to XYZ. So it's absolutely not a diagonal transform. Um, it's got numbers for R and B, which are pretty close to 1. And in fact, the off diagonal elements there are effectively 0. But the Y channel isn't closely related to green. The Y luminance has got 75% green, but it's got 34% red. And here's the wacky part of this transform. It's got minus 7% blue. And it's extremely unusual in any of these matrices to have a negative coefficient into luminance. What this is saying, and this is very wacky and strange and weird, what this is saying is that when you add blue color, ACES blue flavor, to a color, it makes the color less bright. Now, that's absolutely not intuitive. So I need to talk a little bit about why that should be. So what's happening here is that if you remember, I need to pick a higher contrast. Sorry, let me get myself lined up with drawing tools. So you remember the little x, little y chart, and we've got the horseshoe, which is all of the colors, not just all of the colors you can see, because vision is defined, a color is defined by vision. All of the colors are in there. And then we've decided to make ACES RGB have its red primary here, its green primary way up here at little x equals 0, and its blue primary down here. I mean, I should put blue in quotes because physical blue is here. That's the most saturated blue you can make physically. This offset is exactly related to the minus coefficient of luminance. So the blue here is basically sucking yellow out of the luminance. You know, it's the blue, it's so blue that the blue has has got a characteristic that sucks energy out of the medium and long waves. That's the negative luminance coefficient of ACES blue. So it's a mathematical abstraction. By the time you actually see these images, somebody has done some gamut mapping. I mean, you'll never generate pure ACES blue. I mean, no camera will generate that. But because all of the colors lie in the boundaries of the horseshoe. But, you know, you might come up with something a little bit outside the gamut owing to a rounding error or an inaccuracy or a mismatch of camera curves. And, you know, somebody will have to gamut map that or clip that back into the range of colors available, either the range of the colors, you know, if you wish, you could call that an imaginary color. So either non-physical, well, let me give you the three terms: non-physical, non-realizable, or you could also call it imaginary. I mean, in the same sense that, we define I squared equals 1. Um, well, I is, this imaginary number. It's the square root. I'm sorry, I squared is -1. This imaginary number is the square root of -1. It's not a real number. So you could call these imaginary colors. So there's the thing about this ACES transform. It's pretty interesting and kind of wacky. Um, Let me also show you then the transform the other way around. So this is the transform from XYZ to RGB. And you can see that the ACES red it's just a rescaling of the big X. And the rescaling is really associated with the fact that instead of that the white point is chosen a little differently than the assumed white point in the XYZ system. ACES blue is just a rescaled version of big Z. ACES green, well, because of the inverse of the earlier matrix, you've got to decode ACES green by this non-trivial combination of big X, big Y, big Z. Okay, so that covers the transforms of ACES primaries. So now I'm going to very quickly, because I've only got 6 minutes left, very quickly give you a refresher for those of you who heard this in DCT 301 last year, of this 6-page storyboard that talks about how you sense, how you display, what are the spectral characteristics on both sides. So according to the XYZ theory of color science, you ought to, and here I say red sensor, but this is really an X bar sensor, a Y bar sensor, and a Z bar sensor according to color science. This set of graphs gives you the spectral sensitivities of a camera or a scanner that you're supposed to use to deliver big X, big Y, big Z in 3 numbers. So you're supposed to take the spectral content of whatever you're imaging, weight it under those 3 curves, and produce big X, big Y, big Z, 3 numbers. That accurately describes color. So you might say to yourself, okay, we're going to do that. We're going to build the perfect camera. How do we display it? Or more specifically, how do we produce a display that directly is driven by the big X, big Y, big Z signals? What spectral power distributions do we need in that display? And you can go through the CIE color science math and you figure out, well, one thing you figure out, there's a whole huge number of possible spectral signatures of the display because they're 31 element vectors if you have the power represented at intervals of 10 nanometers. So there's not quite, but almost an infinitude of possible answers. But let's say, what spectral power would you use if the spectral power was concentrated at 3 wavelengths? And I chose 470 nanometers, 550 nanometers, and 600 nanometers. And you can go through the mathematics to determine what the power should be, and you get results like this. And this shows you need this much power at 600, this much power for the green primary, which is associated with big Y, and this much power in the blue channel. Problem is there's negative power, which you cannot make physically. So using directly XYZ signals to drive a display Can't be done. I mean, this is the ultimate in wide gamut. It has all of the colors and positive numbers, but you can't display it directly on a display. So flip that idea around and ask, okay, then if I can't display those directly, what can I display? Well, this is the spectral power distribution of a Sony Trinitron CRT. What would I use to sense 3 signals to directly drive that CRT? And this is very, very close to 7 or 9. The answer for what you use at the camera is this. When you do the math and work backward to figure out the camera curves, you get negative numbers. Now, at first glance, you think to yourself, well, that's impossible. I can't do that. But let me run this very brief idea past you that you could actually build a 6-channel camera. One channel generates the positive portion of this curve, and a different channel generates the negative portion. So in other words, we build a camera that senses this, and then electronically we take that and this, we subtract this one electronically to produce that R signal, which will directly drive a trinitron. And for engineering purposes, you can think, well, I mean, in theory, we should really have a sensor sensing that and then electronically inverting it. But for engineering purposes, those 2 negative excursions are so close to 0, you can just call that green. And this excursion is so close to 0, you can just call this blue. So the idea is we have electronic compensation, and that produces the perfect sensing of the scene in just 3 channels. Now, that's the basis for all of the camera processing that you have to do, but it works out that you don't need the 4th channel. That if you choose 3 camera signals appropriately, and you and I don't get to do this, but the camera vendors do. They've got Bayer filters or Prism dichroics that separate the wavelengths out in a certain weighting. And what you do in practice is you take the results of their camera sensitivities. This is an example of a Sony 3CCD dichroic set. And you use electronic circuits to mix those in the correct proportions so that they resemble the ideal theoretical curves. And that is what the 3x3 matrix does. And how you make the 3x3 matrix, we'll do that next class. And basically, let me give you the really quick summary. You start with your camera sensitivities. You look at a color target in the scene like a color checker. You see where the color checker gets mapped according to the device curves, and you do some mathematics to build, to move those colors to the correct places. And you end up with a matrix like this. So this is the sort of 3x3 matrix that you find in an IDT. And we'll talk about the details of building that IDT next class, because we're at the top of the hour. So now I see that Margaret is asking a question, and I really do want to encourage questions. So even though we're just 1 minute over the top of the hour, I'll take maybe 3 minutes and answer Margaret's question now, and we could potentially follow up on this at the beginning of next class, if you wish. Oh, and Peter's asking a question too. So Peter, your question, we might have to do that at the top of next class. So Margaret is asking, is the ColorEdge CG243W, when it's set to wide gamut, displaying SMPTE DCI-P3? And the quick answer is, I don't think so. I think when you set CG243W to wide gamut, that is its description of native gamut. So the native optical properties of the illumination and of the LCD are a little tiny bit wider than P3. And I think, Margaret, you'll find that there is a setting on the 243W for P3. And when you invoke that setting to P3, what the display is doing internally in its signal processing is simply inserting a 3x3 linear light matrix into the path. And that linear light matrix is constructed by exactly the math that I just showed you over the last half hour. So, you know, they've done the work for you, basically. And the 243W and some other comparable displays are calibrated at the factory very, very, very well. And so, you know, if you're in a super, super high accuracy environment, you might want to get a calibrator person in, or maybe if you're a big facility, you've got someone on staff who's got an instrument and knows how to do that. You might want to get someone in to confirm that it is actually delivering those colors. But from the factory, I'm pretty confident that it would be. Now, Margaret, you're also asking about Flanders, which, yes, is a 10-bit panel. I believe it has a SMPTE DCI P3 setting, but I'm not that familiar with that display. You would have to go and really look into the specs to see whether it is actually hitting DCI P3. But it is comparable technology to the ColorEdge. It probably is, but you'll really want to confirm that by making a few measurements before you peg a couple of big VFX jobs on it. So the basic idea is that these emerging displays with RGB LED backlights have got native wide gamut capability, but different native RGB spaces, but they all have, or most of them have, signal processing circuitry built in to do the transforms down to a narrower space. Well, P3 will be typically a little tiny bit narrower than native space. RGB 709 quite a bit narrower than the native space. And it's just 3x3 matrices in the signal path that are doing that for you. So Peter, your question will address at the top of the next hour, next class. So snap that so you can re-ask, because I'm not sure that I can capture my chat transcripts. And that's the end of class 6. So sorry for running 5 minutes over, but again, I'm having a lot of fun doing this, and we'll reconvene. I think we're reconvening 167 hours from now. In other words, same time next week. And I'll see you all then. Thank you so much.